Tonight, I want to take you somewhere you have probably never imagined going. Not outward through the planets, the way most space documentaries take you. Not toward the nearest stars, the way the maps of space usually point us. Tonight, we are going in a different direction entirely. We are going up, and we are going down. Because the solar system you live in is not a sphere. It is a thin disk, a flat disk spinning in space, with the sun at the center and all the planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, orbiting in nearly the same plane, like marbles arranged on a tabletop. We almost never think about what lies above and below that table. We think about what is further out on the table: Pluto, the Kuiper Belt, Voyager, but rarely about what is in the perpendicular direction, the up and the down. And the truth is, the up and the down are stranger and more beautiful and more populated than most of us know. If you went straight up from the sun, perpendicular to the plane in which Earth orbits, what would you find? If you went straight down, in the exact opposite direction, what would you encounter? You would find things that most space documentaries never even mention. You would find scattered icy bodies waiting in regions we are only beginning to map. You would find the soft outer shell of comets that have been drifting for billions of years in patient orbits around our sun. You would find the great galactic plane stretching off in directions we rarely think about. You would find empty corridors of darkness reaching toward neighboring stars. And eventually, if you kept going, you would find the great soft void above our local galactic neighborhood, where almost nothing exists for vast distances. And then, far beyond that, the soft glow of other galaxies drifting in directions perpendicular to our own. Tonight, we are going to take this journey together. We are going to climb out of the plane of the solar system, slowly and gently, and look at what is actually there in the directions we almost never look. And then we are going to come back and go the other way, down, perpendicular and opposite, and see what is on the other side. This is Cosmic Nocturne. Welcome. Get comfortable. Close your eyes if you'd like. You don't need to watch tonight, only listen. Let your breathing slow. Let each breath grow a little softer. There is nothing here you need to remember by morning. This is a slow, gentle drift through the directions of space we almost never think about, the up and the down of the cosmos we live in, told gently enough to carry you toward sleep. Let the world quiet around you. The directions we are going tonight are perpendicular to almost everything you know. They lead away from the planets you have heard about, away from the stars you have seen named in the sky, into regions that astronomers have only recently begun to map, into territories that most space documentaries do not visit. And what is there, in those quiet directions, is more interesting than the silence might suggest. The cosmos is full of strange and gentle things in the up and the down. So, settle in. There's no hurry. Tonight, we are going to learn what is above us and what is below us, in directions you have probably never been told to look. Let me first help you picture the shape of the place you live in. Most of us, when we picture the solar system, see something like a small star at the center with planets orbiting around it. And the planets, in our mind, are often arranged in a kind of three-dimensional cloud, scattered in all directions from the sun. But that is not what the solar system looks like. The real solar system is much flatter than that. It is almost entirely a disk. The sun sits at the center, and the planets, every one of them, orbit in nearly the same plane, a thin, invisible sheet of space that astronomers call the ecliptic. Earth's orbit defines this plane. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune all orbit within a few degrees of this same plane. They are not scattered in a sphere around the sun. They are arranged like marbles spinning on a tabletop, with the sun in the center of the table, and each marble tracing its own slow orbital circle, all in the same flat plane. Why is the solar system flat? The answer is one of the most beautiful pieces of physics in astronomy, and it goes back to the very beginning, 4.5 billion years ago, when the solar system was first forming. In the beginning, there was a great cloud of gas and dust drifting through the galaxy, a soft cosmic cloud slowly turning under its own gravity. As the cloud began to collapse inward toward its own center, something inevitable happened. The cloud was rotating, even very slowly, and as it collapsed inward, the rotation got faster, the same way an ice skater spins faster when she pulls her arms in. And as the rotation got faster, the cloud could not collapse in all directions equally. It could collapse along the rotational axis, where there was no centrifugal force pushing outward. But it could not collapse perpendicular to that axis, where the centrifugal force balanced gravity. And so, over millions of years, the cloud flattened. It became a disk. And in the center of the disk, the gas grew dense enough and hot enough to ignite into a star, our sun. And in the disk around the new sun, the leftover gas and dust gradually clumped together into the planets we now know. This is why the solar system is flat. Every solar system that forms by this same process, and as far as we can tell, all of them do, ends up as a disk, not a sphere. The planets orbit in the leftover disk of material that surrounded the young sun. They have remained in that disk, more or less, for the 4.5 billion years since. And so, when you look at the solar system from far enough away, what you see is not a ball of objects, but a thin, spinning plate, with a star at its center and worlds drifting in its midplane. I find something quiet and beautiful in this. The cosmos has its preferred geometry. When matter collapses under gravity from a rotating cloud, it makes disks. Galaxies are disks. Solar systems are disks. The rings of Saturn are disks. Even the accretion disks around black holes are disks. The cosmos is full of these flat, spinning sheets of matter, made by the same patient physics over and over again, at every scale. Wherever rotation and gravity meet, sooner or later, a disk forms. We live in one of these disks. Our whole solar system is one of these disks. The cosmos, in this sense, has a deep architectural preference for flatness in the places where things are gathering. But here is what this means for tonight's journey. If the solar system is a disk, then the disk has two faces. It has a top and it has a bottom. Above the plane of the planets, perpendicular to the disk in one direction, there is space. Below the plane, perpendicular in the other direction, there is also space. And those two perpendicular directions, the up and the down of the solar system, are places we almost never look. The maps we draw, the orbits we trace, the missions we send, all of them stay close to the plane. We have almost no missions that go up. We have almost no missions that go down. Almost everything humanity has ever sent into space has stayed in the disk. And so the up and the down remain, for most of us, the most unexplored directions of the cosmos. Tonight, we are going to look that way. I want to add something gentle here about how astronomers have come to know all this. The flatness of the solar system was not obvious to ancient observers. For most of human history, we did not have the tools to see that the planets all moved in nearly the same plane. We did not have telescopes powerful enough to map the orbits precisely. It was only with the careful, patient observations of astronomers like Copernicus, Kepler, and Galileo, 400 years ago that the true geometry of the solar system began to emerge. They watched the planets move across the night sky for years. They calculated their positions. They worked out the orbits. And slowly, gradually, the picture clarified. Yes, the planets all move in nearly the same plane. The solar system is a disk. And then, just within our lifetimes, with the development of space-based telescopes capable of looking at other solar systems being born, astronomers have actually photographed protoplanetary disks around young stars. Telescopes like the Atacama Large Millimeter Array, ALMA, in Chile, have captured beautiful images of disks of gas and dust surrounding young stars far across our galaxy. In these images, you can see the disk shape clearly. You can see the dark gaps where young planets are forming, sweeping out their orbital lanes. You can see the structure of how solar systems come to be. Our own solar system once looked like these images. 4.5 billion years ago, when our sun was newly formed, a disk of gas and dust surrounded it, and within that disk, our planets gradually gathered. The flatness of our solar system today is the slowly cooled remnant of that ancient formation disk. We live in the leftovers of the patient, flat process that made us. So, when we go up from the solar system tonight, or down from it, we are leaving the place where the original formation disk lived. We are leaving the place where the planets gathered. We are entering directions that were perpendicular to the formation itself. The perpendicular directions are, in a sense, the directions where the disk was not, where matter never collected, where no planets ever formed. They have been, since the very beginning, the open directions of the solar system, the empty directions, the directions that the original formation process never filled in. And so they remain, today, the directions where we find the most space, the fewest objects, the most patient quiet, the up and the down of a cosmic disk that was born flat and has remained flat for nearly the entire age of the universe. Let us begin by going up. Imagine you are sitting at the center of the solar system, at the sun itself, and you decide to travel straight up, perpendicular to the plane in which Earth orbits, straight out of the disk in the direction we call the North Ecliptic Pole. What would you encounter as you traveled in that direction? For the first long stretch of your journey, you would encounter almost nothing. The space directly above the sun, perpendicular to the ecliptic plane, is one of the emptiest regions in the inner solar system. There is no planet up there. There are no major asteroids. There is no scheduled orbit of any of the objects you have heard about. You would drift through space for billions of miles before you encountered anything substantial at all. The first thing you would notice in this direction is silence. A great, quiet column of space rising out of the disk where everything else is concentrated. But you would not be in pure emptiness. The space above the sun is filled, very thinly, with the solar wind, a soft outward stream of charged particles flowing constantly from the sun in all directions, including up. The solar wind reaches everywhere around the sun, and so, as you climbed perpendicular to the disk, you would be moving through this slow, patient breeze of particles, blown outward from our star at speeds of hundreds of thousands of miles per hour. It is a very thin breeze, only a few particles per cubic centimeter, far thinner than anything we would call atmosphere, but it is there. It is one of the gentlest features of the solar environment, and it extends in all directions, including the perpendicular ones we almost never imagine. As you continued upward, you would eventually leave the region where the solar wind dominates.
Astronomers call this region the heliosphere, the bubble of solar influence carved out of the surrounding interstellar medium by the steady outward push of the solar wind. The heliosphere extends to about 100 times the distance from the Earth to the Sun in most directions. Above and below the disk, the heliosphere extends roughly the same distance as it does within the plane. So if you climbed straight up from the Sun, you would not exit the heliosphere until you reached a great distance, perhaps 100 times the distance from Earth to the Sun, perhaps somewhat less in the perpendicular direction because the boundary is not perfectly spherical. Beyond the heliosphere, you would enter the interstellar medium, the great thin gas that fills the spaces between the stars. This is the same region that Voyager 1 and Voyager 2 are now exploring, although they are exploring it within the plane of the solar system, not above or below it. The interstellar medium above the disk, in our particular direction, is part of what astronomers call the local interstellar cloud, a small cloud of warm gas that our solar system happens to be drifting through right now. It extends in many directions, including above and below us. We are inside this cloud, swimming through it gently as the solar system moves through the galaxy.
And then, far above the cloud, and far above the sun itself, you would eventually encounter something extraordinary. You would encounter the soft outer reaches of what astronomers think is one of the largest structures associated with our solar system. A structure that lives mostly above and below the ecliptic plane, and that we have only indirectly mapped. The Oort cloud. But before we reach the Oort cloud, let me pause and tell you about the one spacecraft that has actually traveled in this perpendicular direction, because it is one of the loveliest and least known stories in the history of space exploration. It is called Ulysses. Ulysses was a spacecraft launched in 1990, jointly built by NASA and the European Space Agency. Its mission was unique. Unlike almost every other spacecraft humanity has ever sent into space, Ulysses was designed to leave the ecliptic plane. It was designed to fly up over the Sun's North Pole and then down under the Sun's South Pole, and to study the solar wind and the solar magnetic field in the perpendicular directions that no spacecraft had ever explored before. To get into such an unusual trajectory, Ulysses first flew out to Jupiter, using Jupiter's enormous gravity as a slingshot to bend its path out of the ecliptic plane. Jupiter swung it dramatically up out of the plane, sending it onto a long elliptical orbit that took it over the Sun's poles, perpendicular to the orbits of the planets. For 17 years, from 1990 to 2009, Ulysses orbited the Sun in this unusual perpendicular trajectory. It made multiple passes over the Sun's North Pole and South Pole, measuring the solar wind, mapping the magnetic field, observing the Sun from angles no other spacecraft had ever achieved. It was a quiet, patient mission. Its discoveries were significant, but rarely made news. Because the perpendicular directions of the solar system are simply less photogenic than the planets. There were no spectacular flyby images of distant worlds. There were no dramatic landings. There was just the slow, patient measurement of the regions above and below the disk, year after year, in a trajectory that no other spacecraft has ever repeated. What Ulysses found, above and below the Sun, was that the solar wind in those perpendicular directions is different from the solar wind in the equatorial plane. The polar solar wind is faster, about twice as fast as the wind in the ecliptic. It comes from regions on the Sun called coronal holes, which extend out of the polar regions of our star. The polar wind is less variable, more steady, blowing out into the perpendicular directions in a more uniform way than the wind in the equatorial plane. Above and below the Sun, the solar environment is gentler and more steady than the busy equatorial regions. I find this lovely. Even the wind of the solar wind is quieter in the perpendicular directions. Ulysses found, in the up and the down of the solar system, a more uniform and patient outward breeze of particles than exists anywhere in the plane of the planets. The perpendicular directions are not just emptier of objects. They are also calmer in the dynamic features that fill the solar environment. Above us and below us, the solar wind blows more steadily. The cosmic weather, in some sense, is gentler. Ulysses ended its mission in 2009, when its electrical systems finally gave out. It is still up there, drifting in its long perpendicular orbit around the Sun, no longer transmitting, but still patiently completing the trajectory it was set on. It will continue to drift in that perpendicular orbit for thousands of years, going up over the North Pole, then down under the South Pole, then up again, in a slow, patient, eternal cycle that no other spacecraft has ever performed. It is a quiet, small monument to the perpendicular directions, drifting up there above the disk where everything else moves. The Oort cloud is one of the most beautiful and least explored features of our solar system. It is a vast, soft, spherical shell of icy bodies, comets mostly, that surrounds our Sun in all directions at enormous distances. It does not lie in the plane of the planets. It extends in every direction equally, above, below, all around, like a great, quiet halo of small frozen worlds drifting in the dark, very far from the Sun, in patient orbits that take millions of years to complete. The Oort cloud is named after Jan Oort, the Dutch astronomer who first proposed its existence in the 1950s, based on a careful analysis of the orbits of long-period comets. the kind of comets that visit the inner solar system only once every few thousand or 100,000 years, and then drift back out into the dark. He calculated where these comets must come from, and the answer was from a vast spherical reservoir extending from perhaps 2,000 to 200,000 times the Earth-Sun distance. That is so far away that the light from the Sun takes nearly 2 years to reach the outer edges of the Oort cloud. 2 years for sunlight, traveling at the fastest speed in the cosmos, to cross from the Sun to the outermost icy bodies of our own solar system. And here is what is most striking about the Oort cloud for the journey we are taking tonight. The Oort cloud is not flat. It is not, like the planets, confined to the disk of the ecliptic. It is spherical, which means that as you climbed straight up from the Sun, perpendicular to the plane of the planets, you would eventually reach the inner edge of the Oort cloud, and you would start passing through soft, icy bodies that drift in orbits very different from the orbits of the planets. There are icy comets above us, drifting quietly in the dark. There are icy comets below us. There are icy comets in every direction around us. The Oort cloud surrounds us like a great soft shell, with billions of icy bodies scattered through it. How many icy bodies are in the Oort cloud? Astronomers estimate that there are perhaps 1 to several trillion icy objects in it, each between roughly the size of a small town and the size of a small mountain, drifting in the dark. Trillions. The number is so large that it is hard to picture. There are likely more icy bodies in the Oort cloud than there are stars in the Milky Way galaxy. Most of them have been there since the very beginning of the solar system, drifting in their long, patient orbits for nearly the entire 4.5 billion years that our Sun has existed. They have not changed. They have not been heated. They have not been disturbed. They are, in some sense, the most pristine surviving samples of the matter that formed our solar system. The original ingredients, gathered in cold storage at the outer edges of our cosmic neighborhood, drifting patiently in the dark, far above and far below and all around the small, bright disk where we live. I find this extraordinary when I let it settle. We picture our solar system as the Sun and a handful of planets. But the Sun and the planets together are a tiny part of the actual solar system. The Oort cloud, the great spherical shell of icy bodies, dwarfs the planetary region in size and in number of objects. The disk where we live is a thin, bright sliver at the center of a vast, mostly empty, mostly spherical region of space, populated thinly with billions of comets, extending from very far out to even farther out. The solar system is, in this larger sense, not a disk at all. It is a sphere, with a thin disk at the center where the planets live. And the great spherical shell around the disk is full of small, icy bodies, drifting in directions we almost never think about, including the up and including the down. Above us, right now, in the perpendicular direction we almost never look, there are billions of icy comets, patient and silent, drifting in the dark. They have been there since before the Earth had a moon. They will still be there long after we are gone. They are some of the quietest and most patient features of our cosmic home. I want to dwell on this for a soft moment, because the temperatures and conditions in the Oort cloud are so different from anything we know that they deserve some attention. Out there, at distances of tens of thousands of times the Earth-Sun distance, the Sun is barely a bright star in the sky. You could look up from the surface of an Oort cloud comet
and see the sun as just one of many points of light in the dark. A slightly brighter one, perhaps, but not the dominating source of warmth and light that we know from Earth. The sun, from that distance, is just another star. And the temperatures in the Oort cloud are extraordinarily cold. The surfaces of those icy bodies sit at temperatures close to absolute zero, perhaps 4 or 5 degrees above it, depending on their exact distance from the sun. They have never been warm. They have never been heated. They have remained at these incredibly cold temperatures for the entire 4.5 billion years they have existed. Their ices, water ice, methane ice, ammonia ice, carbon dioxide ice, and other frozen compounds, have remained frozen in their patient cold orbits since the very beginning. They are some of the coldest objects in our entire solar system.
And in that cold, the chemical composition of the Oort cloud bodies is preserved almost exactly as it was 4.5 billion years ago. They are like cosmic time capsules. The matter that makes them up is the original matter of the protoplanetary disk that formed our solar system, the same material that, closer to the Sun, gathered to form Earth and the other planets. But while Earth's material has been thoroughly cooked and reshaped over 4.5 billion years, melted by the heat of formation, mixed by plate tectonics, weathered by water and air, transformed by life, the Oort cloud material has remained in its original frozen state. When a comet from the Oort cloud is studied carefully, what we are studying is a sample of the very earliest solar system, preserved in cold storage for billions of years. This is one of the reasons astronomers care so much about comets. They are messengers from the deep past, carrying the original chemistry of our solar system in their icy bodies. When a comet sublimates as it approaches the Sun, releasing gas and dust into its tail, we can sample that gas with telescopes and spacecraft and read, in some sense, the original recipe of the solar system. We have done this with several comets in the last few decades, most famously with Comet Halley in 1986, and with comets visited by the Rosetta and Giotto missions. Each gives us a glimpse of the original materials drifting in the dark above us that have been preserved for billions of years. And the distance to the outer edge of the Oort cloud is, in itself, almost incomprehensible. 200,000 times the Earth-Sun distance. That is roughly a quarter of the way to the nearest star, Proxima Centauri. The outer Oort cloud is so far away that it merges, almost, with the territory of other stars. Some astronomers have speculated that the outer Oort clouds of different stars may overlap with each other in interstellar space, occasionally exchanging icy bodies as nearby stars drift past each other through the galaxy. The Oort cloud, in this sense, is not just our solar system's outer shell. It is part of the wider community of icy bodies that surrounds all the stars in our galactic neighborhood. We are not entirely separate from our neighbors, even in the perpendicular directions. The shell of our cosmic home merges, very gently, into the shells of nearby cosmic homes. There is something tender about the Oort cloud, and about the way its comets reach us. Because most of those trillions of icy bodies will never come anywhere near the inner solar system. They will drift in their patient orbits for the entire age of the universe, slowly circling the Sun once every million or 10 million or 100 million years, never approaching close enough to be warmed by sunlight, never developing a tail, never becoming the bright streak in the night sky we call a comet. They will live and die in cold, dark anonymity, far above and far below and all around the bright planetary disk where life happens. But occasionally, very occasionally, one of them is disturbed. Perhaps a passing star, drifting through the galaxy, comes close enough to our Oort cloud to gravitationally tug on one of the icy bodies, nudging it gently into a new orbit. Perhaps the gravitational tide of the galactic disk itself, as our Sun orbits the center of the Milky Way, slowly perturbs the outer Oort cloud and changes the orbits of some of the bodies. Perhaps two icy bodies in the cloud happen to encounter each other, exchanging gravitational pulls. Whatever the reason, every once in a while, one of those trillions of icy bodies has its orbit shifted in such a way that, instead of staying in its long, patient circle, it begins to fall inward toward the Sun. The fall is slow. It takes millions of years. The icy body begins drifting, very slowly, in toward the inner solar system, accelerating gradually as it approaches the Sun's gravity. For most of its long fall, it remains cold and dark and unseen, drifting through space toward our small, bright disk, slowly closing the distance, year by year, century by century, millennium by millennium. And then, finally, after millions of years of slow falling, it reaches the warmer regions of the inner solar system, and the ice begins to vaporize, and a tail begins to form. A soft, luminous tail of gas and dust pushed outward by the solar wind. And the icy body becomes, briefly, a comet. A bright streak visible from Earth. A soft visitor from the patient shell that surrounds us. And then, having swept around the Sun once, it begins the long journey back out, back up, or back down, or back outward in some direction, climbing slowly back toward the Oort cloud from which it came, taking another million years to return. Some comets come from the Oort cloud only once, like this, and never return again. Their orbits, after the close swing past the Sun, become hyperbolic, and they escape from the solar system entirely, drifting off into the spaces between the stars. Others return, to be visitors again, millions of years from now, in a far distant future none of us will see. Every bright comet that has ever crossed our skies, every soft, luminous streak in the night sky that ancient people watched in wonder and modern people photograph with their cameras, came from the Oort cloud, or from the closer Kuiper Belt, which lies in the disk of the planets. But most of the truly long-period comets, the ones that come once and may not return for tens of thousands of years, come from the great spherical shell above and below us. There is something almost lovely in this. The comets that briefly visit our skies are, in a sense, messengers from the up and the down, soft travelers from the directions we almost never think about. Each one is a small, icy survivor from the earliest days of our solar system, gently dislodged from its patient spherical home, taking millions of years to fall inward, briefly visible in our skies for a few weeks or months, and then climbing back out into the dark. We have been receiving these visitors for the entire history of human civilization, and long before. They will keep coming, slowly, one by one, for as long as the solar system exists. They are gentle reminders of the great soft shell that surrounds us in all directions, including up and including down. Let me tell you about some of the famous comets that have visited us, because each one has its own gentle story. Halley's Comet is perhaps the most famous of all, a periodic comet that returns to the inner solar system about every 76 years. It is not technically from the Oort cloud. Its orbit is too short, but it has been observed by human civilizations for at least 2,000 years, recorded in ancient Chinese astronomical records, and in the Bayeux Tapestry, where it appears as a bright streak in the sky over the Norman conquest of England in 1066. Halley returns regularly. Its last appearance was in 1986. Its next appearance will be in 2061. Some of us, perhaps, will see it again. Comet Hale-Bopp in 1997 was an extraordinary comet from much farther out, from the Oort cloud itself. It was visible to the naked eye for 18 months, a soft, glowing streak hanging in the evening sky for an extraordinarily long time. Many people remember it. It returned, for that brief year and a half, from a journey that had lasted thousands of years through the dark, spherical shell above us, briefly visible to humanity, and then drifted back out toward the dark. It will not return for another 2,400 years. The people who will see it again, then, do not yet exist. Comet McNaught, in 2007, was one of the brightest comets of recent decades, visible in daylight from some locations, with a magnificent fanned tail spread across the southern sky. It came from very far out, made a single bright passage past the sun, and is now slowly drifting back outward, having had its orbit changed enough by the encounter that it may never return again. It was a one-time visitor, a single bright evening of cosmic visit from the perpendicular dark. And there have been others. Comet West in 1976, Comet Neowise in 2020, comets visible for shorter or longer periods, each one a brief, soft visitor from the patient shell above and below. Each one came down from the dark for a few weeks or months, sometimes a few years, and then drifted back out to the long, quiet orbits where they came from. We have been receiving these visitors for the entire history of human stargazing. Ancient civilizations made calendars to track them. Modern astronomers photograph them. They have been part of human experience for as long as there have been humans to look up. And every one of them came from the great soft shell that surrounds us in the perpendicular directions. There is something almost sacred about this when I let it settle. The comets that briefly grace our skies are gentle messengers from the directions we almost never look. They have been visiting us for billions of years before there was anyone to notice them. They will keep visiting, slowly, after we are gone. We are part of a long history of receiving these soft travelers from the up and the down. The cosmos has been generous with its visitors. We are part of a great patient relationship with the perpendicular shell that surrounds us.
Now let us turn and go the other way. Let us travel down from the sun, perpendicular to the ecliptic plane, in the opposite direction. What would we find as we traveled toward what astronomers call the south ecliptic pole? Symmetrically, in many ways, we would find similar things to what we found above. The solar wind reaches in this direction too. The heliosphere extends downward in the same shape it extends upward. The Oort cloud surrounds us spherically, so we would pass through icy bodies in this direction as well. Down is, in most ways, the mirror image of up. But there is something slightly different about the down. The plane of the solar system is not perfectly aligned with the plane of the Milky Way galaxy. They are tilted relative to each other by about 60 degrees, which means that if you go straight up from the solar system, you are not heading straight up out of the galactic plane. And if you go straight down from the solar system, you are not heading straight down. You are heading at an angle into different regions of the galactic structure.
When you look up from our solar system, in the direction of the north ecliptic pole, you are looking generally toward the direction of the constellation Draco, the dragon. There are stars in that direction. There are galaxies in that direction. And, very importantly, there are voids in that direction. Soft, empty regions of space where almost nothing exists for vast stretches. The famous Lockman hole, one of the clearest dark windows astronomers use to look out into the universe, is in this region of the sky. Looking up, we look through a region with relatively few stars and very little obscuring gas, and so we can see far into the distant universe in this direction. When you look down from our solar system, in the direction of the south ecliptic pole, you are looking generally toward the constellation Dorado, the goldfish, a small constellation visible from the southern hemisphere. And here, too, there are stars and galaxies in this direction. Very famously, in fact, the large Magellanic Cloud and the small Magellanic Cloud, two small satellite galaxies that orbit our own Milky Way, are visible in roughly this direction. So when you look down from the solar system, you are looking toward two of our nearest galactic neighbors. There is something quietly beautiful about this asymmetry. The up of our solar system points toward distant universe, toward galaxies and voids and the deep cosmic background. The down of our solar system points toward our nearest galactic companions, the soft glow of the Magellanic Clouds, drifting in their slow orbital dance around the Milky Way. The cosmos, by the simple coincidence of how the planes happened to align, gave us different windows in the up and the down. We look up to see far. We look down to see near. And here is something I find tender about the actual missions humanity has sent, both Voyagers. Voyager 1 and Voyager 2 left the solar system in different directions because of the way they had been swung around by gravity assists from Jupiter and Saturn. Voyager 1 is now traveling roughly above the ecliptic plane, in a direction inclined about 35 degrees above the disk where the planets orbit. Voyager 2 is traveling roughly below the ecliptic plane, inclined about 48 degrees below it. The two Voyagers, in some sense, are exploring the perpendicular directions of our cosmic home. One going up and out, one going down and out, gradually parting ways as they sail into different regions of the interstellar medium. This was not exactly planned. The trajectories were chosen primarily to allow the spacecraft to visit specific planets. Voyager 2's famous Grand Tour that took it past Jupiter, Saturn, Uranus, and Neptune required a particular set of gravitational slingshots. But the result of those carefully chosen flybys is that the two Voyagers are now exploring different perpendicular regions of the cosmos. They will continue, for the next many tens of thousands of years, to drift in those perpendicular directions, slowly carrying our small golden records, those engraved discs of human sounds and images that were attached to each spacecraft, into the deep dark above and the deep dark below. There is something almost poetic about this. Without quite intending it, we have already sent representatives of humanity in both the perpendicular directions. Above us, Voyager 1 carries its golden record into the upper interstellar medium. Below us, Voyager 2 carries the same into the lower interstellar medium. We have spread, in a small way, into both the up and the down. We are no longer entirely confined to the ecliptic plane. Our tools have, in some quiet way, reached into the perpendicular directions of our cosmic home. And here's another small fact I find lovely. The down of our solar system also points toward, though this is a more general direction, a region of the galaxy that is somewhat farther from the galactic plane than the up direction. This is because of the way our ecliptic plane happens to be tilted relative to the galactic plane. When you go down from our solar system, you head somewhat more steeply downward through the galactic disk than the up direction heads upward. The down, in some sense, takes you out of the galaxy a little more directly than the up does. The cosmos, by the geometry of how the planes happen to be tilted, gave us a slightly steeper view in the down direction than in the up direction. It is a small asymmetry, but it shapes what we can see in each direction. When astronomers look at the sky to study very faint, distant objects, they often consult these geometric relationships. The cleanest, deep views, the ones least obstructed by our own galaxy's dust and stars, lie in directions that are perpendicular to the galactic plane, and the down of our solar system is roughly in such a direction, though not perfectly. So when astronomers point their most sensitive telescopes downward, perpendicular to the ecliptic, they are pointing towards some of the clearest views of the deep cosmos available from Earth. The Magellanic clouds we mentioned are visible in that direction. Beyond them, the great, soft galactic halo. Beyond that, the deep cosmic web of galaxies stretching for billions of light years. The down is, in some ways, a window into the great cosmic deep. Since we are looking down, let me pause and tell you, gently, about the Magellanic clouds. Because they are some of the most beautiful objects in the southern sky, and they are nearly directly below us in the perpendicular direction we are exploring tonight. The Large Magellanic Cloud is a small, irregular galaxy, about 160,000 light-years from us. It contains perhaps 30 billion stars, a substantial galaxy, though much smaller than our Milky Way, which contains 200 billion stars or more. The Small Magellanic Cloud is even smaller, about 190,000 light-years away, with perhaps a few billion stars. Together, they orbit our Milky Way, drifting in long, slow trajectories around the much larger central galaxy. In the southern hemisphere, on a dark, clear night, both Magellanic clouds are visible to the naked eye. They look like soft, luminous patches in the sky, somewhat resembling small clouds, hence their name. Indigenous peoples in the southern hemisphere have known and named them for thousands of years. They became known in the European tradition through the voyage of Ferdinand Magellan, the Portuguese explorer who first observed them during his circumnavigation of Earth in the 1500s. Their popular name preserves his association, and they are, in their soft way, our nearest galactic companions. There are no other galaxies closer to us than the Magellanic clouds. They are in our cosmic backyard. They have been there, drifting alongside our Milky Way for billions of years. They will continue to drift alongside us for billions more, though current astronomical evidence suggests that the large Magellanic Cloud, in particular, is slowly falling toward the Milky Way and will eventually merge with us hundreds of millions of years from now. I find something tender about this. Looking down, in the perpendicular direction we are exploring tonight, our two small galactic companions drift quietly through the dark, accompanying us on our long galactic journey. They have been with us since before the Earth had life. They have been with us through the long ages of evolution. They have been with us through the rise and fall of every civilization that has ever existed on this small blue world. They will be with us in their slow drifting way until their eventual merging with the Milky Way takes them home into our larger galactic body. They are, in a quiet way, family, our nearest galactic kin, drifting alongside us in the dark, faithful companions of our cosmic home. If you are finding peace in this slow drift through the directions of space we almost never think about, you might take a soft moment to subscribe. It is the easiest way to let the next quiet journey find you, the next time you need somewhere gentle to rest. Then let the thought go and return to the perpendicular directions of the cosmos and to our quiet, drifting companions in the south. I want to share one more soft thought about the Magellanic Clouds before we move on, because there is a feature of them that has only been fully mapped in recent years and that I find quietly extraordinary. There is a great stream of gas connecting the two clouds and stretching out behind them, a long, luminous trail of hydrogen gas that astronomers call the Magellanic Stream. It is hundreds of thousands of light-years long. It was likely created by tidal interactions between the two clouds and with our own Milky Way, gradually pulled out of the smaller galaxies by gravitational forces and stretched into a long, thin filament drifting through the galactic halo. The Magellanic Stream is largely invisible to the naked eye because it is made of cold, neutral hydrogen gas that does not glow in visible light. But when astronomers map it in the radio wavelengths emitted by neutral hydrogen, the stream appears clearly, a great curving arc of gas trailing the two Magellanic Clouds around their slow orbital path. It is one of the largest single structures in our local cosmic neighborhood. It is a kind of ghostly cosmic ribbon,
connecting our two small galactic companions to our larger galaxy, stretching for hundreds of thousands of light years through the dark. I find this extraordinary. Above and below the galactic plane, in directions that overlap somewhat with the perpendicular directions we are exploring tonight, our two small galactic companions are slowly being unwound by gravity. The gas that once made them up is gradually being pulled away, drawn into the larger Milky Way over billions of years. The Magellanic Stream is a record of this slow, patient process, a long, ghostly ribbon of cosmic material being shared from the smaller galaxies into the larger one. By the time the large Magellanic Cloud merges with our Milky Way, much of its gas will have already arrived, gently funneled through this great stream over the eons. We are, in this way, gradually absorbing our cosmic companions. The galaxy you live in is patiently incorporating the smaller galaxies that drift near it, slowly digesting them through gravitational tides over timescales of billions of years. The Magellanic Stream is a snapshot of this process happening now, and the perpendicular directions of our solar system, looking down, looking up, give us views of this slow, patient ingestion of one of the most beautiful, soft cosmic relationships in our local neighborhood. There is something almost familial about this. The smaller galaxies and the larger galaxy are not separate. They are connected, gravitationally, gastronomically, in the long, patient way that cosmic structures form and reform each other. The Magellanic Clouds are not just neighbors. They are slowly becoming part of us over billions of years as their gas drifts down the long stream and into our larger galactic body. By the time they have fully merged, much of their substance will already have arrived. We will absorb them gently, gravitationally, patiently, in a process that has already begun and that will continue, slowly, for billions of years to come. The down of our solar system, when you look long enough, is rich with these slow, patient cosmic processes. Two small galactic companions drift below us in the perpendicular direction. A great, ghostly stream of gas connects them to us, stretching for hundreds of thousands of light years through the dark. They are not strangers. They are family in slow, gravitational merger. They have been with us for billions of years. They will be with us in their slow drifting way until their bodies join ours. Let me now widen the lens. Because the solar system, with its disk of planets and its spherical shell of Oort cloud comets, is itself sitting inside something much larger, the Milky Way galaxy. And the Milky Way, too, is a disk, a much larger disk, a vastly larger disk. And our solar system sits inside that larger disk, in a position that I think is worth pausing on, because it tells us something quiet and beautiful about where we live. The Milky Way galaxy is a flat, spiral disk, about 100,000 light-years across, containing somewhere between 2 and 400 billion stars. Our solar system is one of those stars, a single, small sun, surrounded by its planets and Oort cloud, drifting through the disk of the galaxy at a particular location. We are located about 26,000 light-years from the center of the galaxy, in one of the outer spiral arms. We are not at the center. We are not at the edge. We are somewhere in the middle, in the patient orbital flow of the galaxy.
And here is the part I find lovely. Our solar system sits inside the galactic disk, but slightly above the midplane of the galactic disk. The galactic disk has a thickness, It is not a perfect mathematical plane, but a thin, three-dimensional region with stars distributed in it. Our Sun lies about 60 to 70 light-years above the midplane of the disk, slowly drifting upward through the disk in the direction of the constellation Hercules. We are not at the geometric center of the galactic disk in the vertical direction. We are slightly above it, like a small object floating above the floor of a great spinning room. And we are slowly bobbing. As the Sun orbits the center of the galaxy, taking about 225 million years to complete one orbital circuit, it does not move in a perfect circle in the midplane. It oscillates gently up and down through the midplane, crossing it about every 30 million years, rising above it for 15 million years, sinking below it for 15 million years, in a slow, patient, cosmic bob. We are, right now, slightly above the midplane and slowly rising. We will continue to rise for a few million more years before we begin to fall back. And then, after another 15 million years, we will be below the midplane. And so the cycle continues, over and over again, throughout the entire history of the solar system. This is happening right now, in directions that lie roughly perpendicular to the ecliptic plane we have been exploring tonight, but tilted by about 60 degrees from it. Our solar system is moving gently up through the galactic disk. Every star you can see in the night sky is moving in similar, patient, cosmic motions, each tracing its own slow, bobbing orbit around the center of the galaxy. The Milky Way is alive with this gentle motion. Every star in it is rising or falling or oscillating, all in their own long timescales, none of them at rest, all of them in patient gravitational flow. And as the Sun bobs up and down through the galactic disk, the perpendicular directions we have been exploring tonight, the up and the down of our solar system, change their relationship to the galaxy. Right now, the north ecliptic pole points slightly downward through the galactic plane. The south ecliptic pole points slightly upward through it. Over millions of years, as the Sun rotates and precesses, and as the galaxy turns around it, these relationships gradually shift. The directions we are looking tonight, the up and the down of the solar system, are not fixed forever. They are part of a slowly changing geometric dance with the larger galaxy around us. I want to dwell on this for a soft moment, because the slow bobbing of our solar system through the galactic disk is one of the loveliest, patient motions in nature, and it may have effects on life on Earth that astronomers are still working to understand. Every 30 million years or so, as the Sun completes one full cycle of bobbing up and down through the midplane of the galaxy, our solar system passes through regions where the density of interstellar gas and dust changes. The midplane of the disk is denser than the regions above and below it. So, as we cross the midplane every 15 million years, we are temporarily in a slightly more crowded part of the galaxy, passing through more gas, more dust, more nearby stars than when we are far from the midplane. The crossing takes only a few 100,000 years, but during that time, the cosmic environment around the Sun is gently denser than during the rest of the bobbing cycle. Some astronomers have proposed that these regular crossings of the galactic midplane may correlate with certain features of Earth's history, perhaps periods of increased comet activity, perhaps periods of increased meteor impacts, perhaps even some of the mass extinction events in Earth's deep past. The idea is that when we pass through a denser region of the galactic disk, we may be more likely to encounter nearby stars whose gravity could perturb the Oort cloud, dislodging additional icy bodies and sending more of them on the long, slow fall inward toward the inner solar system. More comets,
more potential impacts, possibly more cosmic disturbance during the periods of crossing.
The evidence for this is still debated. Mass extinctions on Earth do not perfectly correlate with the timing of mid-plane crossings, and there are many other possible causes of extinctions. But the idea that the slow bobbing motion of our Sun through the galaxy might leave traces in the geological record of life on Earth is one of those quietly extraordinary connections between cosmic motion and terrestrial history. Even the deep, slow motions of our cosmic home, taking tens of millions of years to complete one cycle, may have left their imprints on the story of life on this small blue world. And here is the gentlest part of this. Our current bobbing motion places us, right now, in one of the relatively safe regions of the cycle. We are slightly above the midplane, slowly rising. We will not cross the midplane again for several million years. The cosmic neighborhood we are passing through right now is relatively quiet. Fewer nearby stars than during midplane crossings. Less interstellar dust. Less of everything that might gravitationally disturb the Oort cloud above and below us. We are, by the gentle accident of where we are in the bobbing cycle, in a quieter cosmic moment than we will be in 15 or 30 million years. The cosmos times its slow motions on scales that exceed human experience. We will never see the full bobbing cycle. We will never witness one complete passage through the galactic midplane and back. The whole motion takes 30 million years. Humanity has existed for less than 2 million. We are nestled inside a cosmic motion so slow that it is barely perceptible even on geological timescales. But it is happening. The Sun is rising gently through the galactic disk, taking us with it, and in a few million years, it will reach the upper limit of its current bobbing motion and begin to fall back. The cosmos, in this sense, has its long, patient rhythms going around us all the time. We are not stationary observers. We are passengers on a slow, bobbing vehicle through the great galactic disk. If we kept going, all the way up out of the solar system and on through the Oort cloud and out into interstellar space, and we kept going all the way out beyond the local stars, and we kept going, what would we eventually find above and below the galactic plane itself? This is one of my favorite questions in astronomy because the answer is surprising and beautiful. Above and below the Milky Way, the cosmos looks very different from how it looks within the plane of the galaxy. Inside the plane of the Milky Way, you are surrounded by stars, gas, dust, and other galactic material. When you look toward the center of the galaxy, you see the great bright band of the Milky Way arching across the sky. That soft, luminous strip of stars and dust visible from dark places on Earth. When you look outward through the galactic disk, you see fewer stars, but still considerable gas and dust between them. The galactic disk is a busy place. It is full of matter. But above and below the galactic disk, perpendicular to its flat plane, the matter density drops dramatically. The space above and below the galactic disk is largely empty. There are very few stars in those directions. There is very little gas. There is very little dust. You are looking out through a soft, thin region of the galaxy's outer halo, and then beyond it, out into the great intergalactic dark. This is why, when astronomers want to look at distant galaxies, they often choose to look in the perpendicular directions, up out of the galactic plane or down out of the galactic plane. The view in those directions is clearer than the view through the galactic disk. The galactic plane is full of obscuring gas and dust that block our view of objects beyond it.
The perpendicular directions are largely transparent. The famous Hubble Deep Field, the most distant image of the universe ever taken, looked in a direction that was nearly perpendicular to the galactic plane, where the view out was unobstructed. So when you stand outside on a dark night and look up at the sky, the direction in which you can see farthest into the universe is, roughly speaking, perpendicular to the band of the Milky Way. If you turn your head so the Milky Way's soft, luminous strip is running horizontally across your view, and you look straight up, you are looking out of the galactic plane and into the great cosmic distances beyond. In that direction, the view is clearer than anywhere else. The deep universe lies mostly above and below us in the galactic perpendicular directions. The disk of the galaxy obscures the view in its own plane. The transparent directions are the ones away from the plane.
And so, looking far up, through the Oort cloud above us, then through the local interstellar medium, then through the soft outer reaches of the Milky Way's halo, then out into the great intergalactic void, eventually you would see distant galaxies. Thousands of them, millions of them, the great clusters and superclusters of galaxies that fill the universe. Galaxy after galaxy after galaxy, scattered through the deep dark in vast patterns we are only beginning to map. The universe, in the perpendicular directions, opens up into a vast, soft library of other galaxies, all drifting in their own patient ways. I find this strange and beautiful. The directions we almost never look when we are thinking about space turn out to be the directions through which we can see the most. The up and the down of the solar system, when extended far enough, lead us out of the busy galactic plane and into the great quiet spaces between galaxies, where the universe shows itself most clearly. The cosmos is more visible in the perpendicular directions than in any other direction. The view is clearer. The reach is longer. The deep dark is most accessible from the up and the down. I want to add a soft thought about what lies in the galactic halo, the region of the galaxy above and below the bright disk, because it contains some of the most beautiful features of our cosmic home, even though they are dimmer and harder to see. The galactic halo is a roughly spherical region surrounding the bright disk of the Milky Way. It is much less dense than the disk. There are fewer stars in the halo, less gas, less dust. But it is not empty. It contains some of the oldest stars in our galaxy. It contains globular clusters, tight spherical groupings of hundreds of thousands of ancient stars gathered together in compact bodies that drift in long elliptical orbits around the center of the galaxy. There are about 150 known globular clusters in the Milky Way's halo. Each one is a small, ancient population of stars formed early in the history of our galaxy, drifting now in the perpendicular regions above and below the disk. These globular clusters are extraordinarily old. Some of them contain stars that are nearly as old as the universe itself, 12 or 13 billion years old. They formed in the very earliest days of our galaxy's history, gathered together by gravity into compact spherical groups, and they have been drifting in their long orbits ever since. They are the elders of the galaxy, the patient, ancient bodies of stars that have witnessed the entire history of our galactic home. When you look up from Earth at the night sky, in certain directions perpendicular to the galactic plane, you can sometimes see globular clusters with the naked eye on dark nights. Omega Centauri, the largest known globular cluster, is visible from the southern hemisphere as a faint, fuzzy patch, a soft, luminous cloud that, when viewed through a telescope, resolves into hundreds of thousands of individual ancient stars. 47 Tucanae, another beautiful cluster, is also visible from the south. The Hercules cluster, M13, is visible from the north. Each of these is an ancient population of stars drifting in the halo above or below the galactic disk, having been there longer than almost anything else we know. I find it moving to think of these globular clusters as old witnesses. They have been drifting in their long orbits since the very early universe. They have seen our galaxy form. They have seen the disk of the Milky Way settle into its current shape. They have seen the Sun form 4.5 billion years ago in some patient corner of the disk. They have seen the Earth form, and the Moon, and the first life. They are still there, drifting in the perpendicular directions, doing nothing more than being themselves, ancient and patient, in the dark spaces above and below the bright galactic plane. Beyond the globular clusters, the galactic halo extends outward into the dark matter halo, the much larger spherical region of dark matter that surrounds our entire galaxy. The dark matter halo extends to perhaps 100 or 200,000 light-years above and below the disk, encompassing not just our visible galaxy, but the smaller satellite galaxies that orbit it. The dark matter halo is invisible. We cannot see it directly, but we can detect it through its gravitational effects on the visible matter around it. Our entire galaxy is nestled inside this much larger dark matter cocoon, which extends generously in the perpendicular directions above and below the disk. Above and below us, then, in directions we almost never look, we have ancient stars gathered into globular clusters that have drifted patiently for billions of years. We have a great invisible halo of dark matter extending generously into the perpendicular dark. The galactic halo, in some sense, is the patient, quiet shell of our galactic home, the place where the oldest things live, where the dim and ancient bodies drift, where the invisible mass of the galaxy gently extends into the perpendicular directions. It is, in its quiet way, beautiful. There is another feature of our solar system that depends on the perpendicular directions, and I want to share it with you, gently, because it is one of the lesser known but most beautiful structures associated with our cosmic home. It is called the Bowshock, or more precisely, it is the leading edge of the heliosphere, the region of space carved out by the solar wind, as the solar system moves through the surrounding interstellar medium. The Sun is not stationary. It is moving through the galaxy at considerable speed, about 520,000 miles per hour, relative to the local interstellar medium around us. The Sun, and everything attached to it, including Earth and the entire solar system, is drifting in a particular direction through the soft gas that fills the spaces between the stars. We are not floating still, we are sailing. And as the solar system sails through the interstellar gas, the front of the heliosphere, the leading edge in the direction we are moving, gets compressed. The gas in front of us piles up gently against the heliosphere boundary, the way water piles up against the front of a moving boat. Behind us, the heliosphere stretches out into a long, soft tail, like the wake behind a boat. The whole heliosphere is not a sphere, despite its name. It is more like an elongated bubble, compressed in the front and stretched in the back, drifting through the interstellar gas in the direction we are moving. The direction we are moving, by the way, is roughly toward the constellation Hercules. We are sailing through the galaxy toward Hercules at a few hundred miles per second. This direction is not in the plane of the ecliptic.
and not perfectly aligned with the galactic plane either. It is at its own angle, set by the specific orbital motion of the Sun around the galactic center, plus the local random motion of the Sun within the galactic neighborhood. Tonight, somewhere in the direction of Hercules, the heliosphere is being compressed by our motion through the interstellar gas. And on the opposite side, somewhere far behind us, the heliotail is stretching out for hundreds of times the distance from Earth to the Sun, a long, soft wake of solar wind drifting back through the cosmos.
Voyager 1 and Voyager 2, which we spoke of in an earlier video, have actually crossed the heliopause, the outer boundary of the heliosphere, in the leading direction. They are now in interstellar space, on the side where the heliosphere is compressed by our motion. They have traversed the great soft front edge of our cosmic bubble and are now drifting in the interstellar medium beyond. The perpendicular directions, the up and the down of the ecliptic, are not the directions we are moving in. They are perpendicular to our motion, which means that the heliosphere, in those perpendicular directions, is neither compressed nor stretched, but at its more average shape. Above us and below us, the heliosphere extends to roughly its standard radius, neither shrunk by motion nor extended by wake. Above us and below us, the heliosphere is in its quieter, more balanced configuration. The drama is happening in the leading and trailing directions, not in the perpendicular ones. I find this lovely. The up and the down of the solar system, in addition to being the directions we almost never look, are also the most peaceful directions in the heliosphere, neither compressed by the wind of our motion, nor stretched by the wake we leave behind. They are the quieter directions of our cosmic vehicle as it sails through the interstellar dark. Wherever we are going, the up and the down are perpendicular to it. They are the calm sides of the great drifting bubble of solar wind that surrounds us. There is also a spacecraft mission that has been mapping this great heliosphere structure for the last 15 years or so, and I want to tell you about it briefly, because it is one of the loveliest small missions in space history. It is called IBEX, the Interstellar Boundary Explorer. Launched in 2008, IBEX is a small spacecraft orbiting Earth, designed to detect particles that come back inward from the outer boundaries of the heliosphere, the place where the solar wind meets the interstellar medium. What IBEX discovered, after years of patient observation, was that the boundary of our heliosphere is not uniform. There is a bright, narrow ribbon of energetic particles coming from a particular direction at the boundary, a sharp line of intensity that astronomers had not predicted. It is now called the IBEX ribbon. It runs across the sky in a long arc, and astronomers are still working to understand exactly why it exists. But the leading theory is that the IBEX ribbon traces the place where our local magnetic field is perpendicular to the magnetic field of the interstellar medium around us. The ribbon is, in some sense, a magnetic map of how our heliosphere meets the surrounding interstellar gas. The ribbon stretches across both the up and the down of the solar system, in different segments. It is one of the largest single structures associated with the boundary of our cosmic home, and it was completely unknown until IBEX began observing. We are still learning what it is. We are still learning why it has the shape it has. The cosmos is still revealing the structure of its boundaries to us, even in our own immediate neighborhood, in the directions just above and just below the solar system. There is something almost beautiful about this. Right now, in the perpendicular directions above and below us, energetic particles are streaming inward from a great bright ribbon at the edge of our heliosphere.
The ribbon was unknown to anyone before 2008. The cosmos has soft features, even very close to home, that we are only now beginning to map. Above us and below us, the boundary of our cosmic bubble has a structure that no one expected, and that we are still working to understand. We are still discovering our own neighborhood. Even after centuries of careful astronomical observation, the perpendicular directions of our solar system continue to reveal small, soft surprises. The ibex ribbon is one of them. There will likely be others. The cosmos, even very close to home, has more in it than we know. There is something else above and below us, in a region that astronomers have been mapping more carefully in recent years, that I want to tell you about because it is one of the most beautiful and least known features of our cosmic neighborhood. It is called the local bubble, and our solar system sits inside it. The local bubble is a large region of space, about 1,000 light-years across, that is unusually empty of gas and dust. The rest of the local interstellar medium, in our area of the Milky Way, has a typical density of about 1 atom per cubic centimeter of gas. Inside the local bubble, the density is much lower, closer to 1/10 of that. So we are sitting in a kind of bubble of relatively empty space, surrounded by walls of denser gas farther out. How did the local bubble form? Astronomers believe it was carved out by a series of supernova explosions over the past few million years. Each supernova blew a small bubble of gas outward. Successive supernovae, exploding in nearby regions of the galaxy, expanded and joined their bubbles together, gradually carving out a large, irregular cavity in the interstellar gas. We are now inside that cavity. The walls of the cavity, where the swept-up gas accumulates, surround us in all directions, including above and below. What is most striking about the local bubble, when you map it carefully, is that it is not a simple sphere. It has a complicated three-dimensional shape, with openings and extensions that lead in different directions, some of which connect to other nearby cavities in the interstellar gas. Above and below the galactic plane, the local bubble has chimney-like extensions that reach up and down into the surrounding gas. These are sometimes called galactic chimneys, openings in the interstellar gas that connect the dense galactic disk to the much sparser galactic halo above and below. If you climbed straight up from our solar system, far past the heliosphere, past the Oort cloud, past the local interstellar medium, you would eventually find yourself inside one of these galactic chimneys, climbing through a long, soft cavity in the interstellar gas, with denser walls on either side, leading slowly upward toward the much emptier galactic halo. And similarly, straight down, you would find another chimney, leading slowly downward into the lower halo. I find something wonderful in this. We live not just inside a flat solar system disk, and not just inside a flat galactic disk, but inside a bubble within a chimney. The chimney connects the busy plane of the galaxy to the quieter regions above and below it. And the bubble within the chimney is our soft local neighborhood, where the gas is thinner than average, where the supernovae that carved it out happened far enough in the past that we did not see them, but their effects shaped the very space we now live in. The cosmos, when you map it carefully, is full of these intricate three-dimensional structures, layered inside each other at every scale. Solar system inside Oort cloud inside local interstellar cloud inside local bubble inside galactic disk inside the larger galactic halo. Each layer with its own particular geometry, its own particular history, its own particular relationship to the layers around it. We sit, somewhere deep in this nested structure, looking out through it in all directions, including up and including down. And here is a soft fact about the local bubble that I find moving. The supernovae that carved it out happened over the last 15 million years or so. The most recent of them probably exploded around 2 or 3 million years ago, well within the time when there were already early humans on Earth, though they would have been our hominid ancestors, perhaps Australopithecus or early Homo, not modern humans. Some of those ancient ancestors might have looked up and seen, in their night sky, a sudden, bright new point of light appearing where no star had been before. The supernova explosions that shaped the local bubble we now live in were visible from Earth, briefly, as bright new stars in the sky, 2 or 3 million years ago. We do not know if any ancient hominid noticed. We do not know if anyone, watching the sky in those long-ago nights, marked the appearance of an unusually bright star and wondered at it. But the supernova was there. It exploded somewhere in our cosmic neighborhood, and for a few weeks or months, its light would have been visible from Earth. Brighter than Venus, perhaps brighter than the full moon, hanging in the sky for an unusually long time, and then slowly fading away. The light from that ancient explosion has long since passed beyond Earth, but its effects shaped the very space we now drift through. The local bubble is the slowly cooled remnant of that ancient cosmic event. I find this almost tender. The space we live in now, the relatively empty bubble through which our solar system is drifting, was carved by ancient explosions that some of our most distant ancestors might have seen. The cosmos that surrounds us has been shaped by events that happened just a few million years ago in cosmic time, long ago by human reckoning, but very recent by stellar standards. We are drifting through a structure made by stars that exploded within the lifespan of the human evolutionary tree.
And the chimneys that lead from the local bubble up and down through the galactic disk are gradually changing. As our sun continues to bob through the galaxy, our position in the local bubble shifts. We are not at the geometric center of the bubble. We are off-center. And as the centuries pass into millennia, into millions of years, we will drift through different regions of the bubble, eventually approaching its walls, eventually crossing them, and entering whatever lies beyond. The cosmos has its slow, patient timetables. The local bubble is our home for now, but it is not our home forever. Eventually, in millions of years, we will leave it and enter whatever region of denser interstellar gas surrounds it. The cosmos has its long, slow, gentle drifts, and we are part of one of them. For tonight, though, we are at the center of our bubble. We are drifting through the relatively quiet, thin gas of our local neighborhood. Above us, the chimney extends upward into the lower galactic halo. Below us, another chimney extends downward into the lower halo. Around us in every direction, the soft walls of the bubble surround us at distances of hundreds of light years. We are nestled, gently, in a quiet, local region of the galaxy, drifting through it slowly as the larger galactic rotation carries us forward through the dark. Up out of our galaxy, in the perpendicular direction we are exploring tonight, there is something very strange that has been gradually mapped in the last decade or so. There are objects above and below the Milky Way that may be entire galaxies, full structures with the gravitational mass of galaxies, but containing almost no stars. They are called dark galaxies, and we are only beginning to understand them. For a long time, astronomers assumed that wherever there was a large amount of dark matter, the mysterious, invisible substance that makes up most of the matter in the universe, there would also be stars. After all, dark matter forms clumps that pull gas into them, and gas,
when it gathers densely enough, forms stars. So, big clumps of dark matter should have lots of stars. Smaller clumps, fewer stars. But every clump should have at least some stars. That was the assumption. But in the last decade or so, astronomers have found, in the regions above and below the Milky Way, what appear to be substantial clumps of dark matter that contain very few stars at all. Sometimes only a few dozen stars in an entire structure that has the gravitational mass equivalent to millions of solar masses. These are the dark galaxies. They are like dim ghosts orbiting our Milky Way, pulled toward us by gravity, but almost invisible because they contain so little light-emitting matter. How do we know they are there at all? We see them through their gravitational effects, mostly. The way they perturb the motions of nearby, visible stars. The way they bend light from distant background galaxies. The way they orbit our Milky Way as small, dim companions. Each detection is difficult. Each is uncertain. But the gathering evidence suggests that the cosmos may be full of these dim companion galaxies, especially in the perpendicular directions above and below the galactic plane, where the small companions cluster and orbit. I find this almost spooky and quite lovely. Above us, in the perpendicular direction we are exploring tonight, there may be entire galaxies, substantial gravitational structures with the mass of millions of suns, drifting in patient orbits around the Milky Way, almost completely dark. We cannot easily see them. We cannot easily photograph them. They are there, but they are very nearly invisible, and we are only beginning to map them. The cosmos is, in this way, full of things we are still discovering, even in directions we have looked at for centuries. The up of the solar system, when you map it carefully and look long enough, has more in it than we knew. The down does too. The perpendicular directions of our cosmic home contain populations of dim galaxies that we are only now beginning to identify. And if it moves you to think of these soft, dim companions above and below us, drifting in patient orbits around our galaxy, I would gently invite you, in the comments below, to leave a single word, something that lingers from this drift through the perpendicular directions of the cosmos. A word from the up, a word from the down, whatever the night has given you. A small gathering of words from everyone listening tonight, marking what we noticed together in the directions we almost never look.
And then let the thought go and return to the slow, gentle drift through the directions above and below. I want to dwell on the dark galaxies a moment longer, because the discovery of these dim companions has been one of the quietest and most beautiful astronomical stories of the last decade. The first hints came from the careful analysis of the orbits of stars in our galactic neighborhood. Some stars were moving in ways that suggested the presence of large, unseen gravitational masses pulling on them. The masses were too large to be ordinary dim stars. They had to be something else, large concentrations of matter that did not glow. Astronomers gradually worked out, through careful, patient observation, that these unseen masses were entire small galaxies. Galaxies made mostly of dark matter, with very few stars. Some of them were given names. The Crater 2 dwarf galaxy, the Antlia 2 dwarf galaxy, the Bootes 1 dwarf galaxy. Each one was a dim, small companion orbiting our Milky Way, almost invisible because it contains so few stars, but detectable through its gravitational influence on the surrounding visible matter. What is most beautiful about these dark companion galaxies is that they may be the survivors of an ancient cosmic process. In the very early universe, dark matter clumped together first, forming small gravitational structures that we now call dark matter halos. Then, ordinary matter, gas, dust, fell into those dark matter halos, gathered, formed stars, and made visible galaxies. But not every dark matter halo successfully made stars. Some of them remained mostly dark, with only a few stars forming in them. Those are the dim companion galaxies we are now discovering. They are, in some sense, the cosmic firstborn, the dark matter structures that came first, before stars learned to gather inside them. They are still there, drifting in our galactic halo, patient and dim, mostly invisible. I find this almost moving in a way I find hard to describe. The cosmos has populations of nearly invisible galaxies drifting in patient orbits around us. Soft, dim, cosmic companions that have been there since the very early universe, that we are only now beginning to see. They are not threats. They are not strange. They are simply what was here first, the patient, dark structures of the cosmos, holding the original imprint of the universe's dark matter distribution, drifting in the perpendicular directions where the galactic halo extends. Above us, in the perpendicular direction, dim companion galaxies orbit slowly. Below us, the same. They are family in their dim, quiet way, the ancient siblings of our Milky Way, formed from the same primordial soup of dark matter, but never quite gathering enough ordinary matter to ignite into bright galactic bodies. They have been our patient, dim neighbors since the universe was young. They will continue to drift around us, patient and dark, for as long as the universe exists. We are not alone in our galactic halo. We are surrounded, in all the perpendicular directions, by these soft, dim companions, invisible to the naked eye, almost invisible to most telescopes, but there, patient and quiet, in the dark above and below us. They have been there since long before us. They will be there long after us. They are part of the cosmic family we share our galactic home with, in their gentle, dim way. Let me now take you somewhere very specific in the perpendicular directions, because I want to anchor this journey in a concrete cosmic relationship. Above the plane of the Milky Way, in a direction that is somewhat perpendicular to our galactic disk, and not too far from the perpendicular direction out of the solar system, lies one of the most famous objects in the cosmos, the Andromeda Galaxy. Andromeda is the nearest large galaxy to our Milky Way. It is about 2.5 million light-years away, meaning the light reaching us from it left more than 2 million years before any human civilization existed. The light from Andromeda that you can see tonight, if you go outside in a dark place in the northern hemisphere and look toward the constellation of Andromeda, left that galaxy when our ancestors were just beginning to use stone tools. 2.5 million years of patient travel through the dark. Andromeda is a spiral galaxy similar to our Milky Way, but slightly larger. Perhaps 1 trillion stars to our 200 billion. It contains its own central supermassive black hole, larger than our own. It contains its own spiral arms, its own central bulge, its own halo of dark matter and dim companion galaxies. It is, in many ways, a sister to our own galaxy, born of the same cosmic processes, evolved over similar timescales, structured in similar ways. And here is what is most striking.
Andromeda is moving toward us, slowly, patiently, gravitationally. The Andromeda Galaxy and the Milky Way are drifting toward each other through the dark, drawn by mutual gravitational attraction. The relative motion is about 250,000 miles per hour. At that speed, the two galaxies will meet in about 4 billion years. When they meet, the merger will not be the violent collision we sometimes picture. Galaxies are mostly empty space. The individual stars are so far apart that almost none of them will actually collide. Instead, the two galaxies will gradually drift through each other, their stars passing each other in the vast spaces between, the gas clouds being more disturbed than the stars. Over billions of years, the gravitational interplay will reshape both galaxies, mixing them, eventually merging them into a single, larger galaxy that astronomers sometimes call Milkomeda. By that time, our Sun will have aged considerably. The Earth may no longer be habitable. The merger itself will be a slow, patient gravitational waltz that takes much longer than any human civilization could observe. But the merger has already begun, in a sense. The two galaxies are already approaching. Every year, Andromeda and the Milky Way are about 300 billion miles closer than they were the year before. Tonight, in the direction of the constellation Andromeda, our sister galaxy drifts toward us in the dark. The slow gravitational dance is happening as we breathe. I find this almost unbearably tender. The cosmos contains, far above our galactic plane, our nearest large galactic sibling, drifting through the dark, slowly approaching, fated to merge with us in 4 billion years. We are not alone in our perpendicular direction. We have a great, soft galactic companion drifting toward us, patient and inevitable, in a meeting that no being on Earth tonight will witness, but that the cosmos has been preparing for billions of years. If these gentle drifts are bringing you peace, subscribing is the surest way to let the next one find you on another night when you need somewhere quiet to rest. Then let the thought go and return to Andromeda, drifting silently toward us in the dark, and to the slow, patient cosmic motions that surround us in every direction. There is something specific about how we can see Andromeda from Earth that I want to share, because it brings home, in a soft way, how the perpendicular directions open up to the universe. On a dark, clear night in the northern hemisphere, in autumn, you can find Andromeda in the sky if you know where to look. It is one of the few galaxies visible to the naked eye from Earth. It appears as a soft, luminous patch, somewhat elongated, in the constellation of Andromeda. It is faint. You need a dark sky to see it well, but it is there. 2.5 million light-years away and visible to the naked eye, drifting toward us in the dark. When you look at Andromeda with the naked eye, you are seeing photons that left it 2.5 million years ago. The photons that hit your eye traveled through the great void between galaxies for 2.5 million years, finally arriving at this small blue world to be detected by the rods and cones at the back of your eye. You are receiving light older than humanity itself. The light hitting your retina is older than our species.
The largest single structures in the universe are billions of light-years across. We are nestled, like a small mote of dust, inside a galaxy, inside a local group, inside a supercluster, inside Laniakea, inside the cosmic web, inside the observable universe. And the perpendicular directions of our solar system, the up and the down we have been exploring tonight, lead us eventually out into this larger structure where the universe shows itself most clearly. It is hard not to feel small when you think about this, but I find that the smallness is part of the gentleness. The cosmos is much bigger than we are. The structures into which we are nested extend far beyond what we can directly perceive. And yet here we are, on a small blue world inside one of those structures, looking out through the layers, slowly figuring out our address in the great, soft architecture of existence. We are very small. We are also very precisely placed. We are nested inside structure after structure after structure, each with its own beauty, each contributing in its own way to the cosmos we live in. If these quiet drifts through the cosmos help you rest, subscribing is the easiest way to let me find you again on another quiet night. The cosmos has been here, in its great, soft, layered architecture, for billions of years. These nights try, in their own small way, to keep arriving faithfully. Then let the thought go and return to the deep, gentle, perpendicular directions of the universe we live in. I want to share one more soft thought about the cosmic web before we leave it, because it is one of the most beautiful pictures of the universe that modern astronomy has produced. When astronomers map the distribution of galaxies in the universe, locating millions of them and plotting where they sit in 3 dimensions, what emerges is a structure that looks almost biological. The galaxies are not scattered randomly. They cluster along long, thin filaments. The filaments connect at junctions, where superclusters of galaxies gather. Between the filaments are vast, empty voids, soft regions hundreds of millions of light-years across that contain almost no galaxies at all. The whole pattern, mapped at the largest scales, looks something like a great cosmic foam, or a sponge, or a neural network. Long, thin filaments separated by enormous, empty bubbles. This is the cosmic web. And the most extraordinary thing about it is that the same overall pattern repeats at every scale. Small filaments lie within larger filaments. Small voids lie within larger voids. The cosmic web is, in some sense, fractal, self-similar across vast ranges of scale. The universe has chosen this strange, beautiful architecture for itself. And our small galactic neighborhood is part of one of these filaments. We sit inside a filament called the Virgo supercluster, which is itself part of a larger structure called the Laniakea supercluster. Laniakea contains about 100,000 galaxies and stretches across 500 million light-years. The name Laniakea comes from Hawaiian, meaning immeasurable heaven, a name chosen by the astronomers who first mapped the supercluster's full extent, in honor of the Polynesian navigators who traveled vast distances by reading the sky. Beyond Laniakea, in the perpendicular directions we have been exploring, are other superclusters: the Perseus-Pisces supercluster, the Coma supercluster, the Shapley supercluster, and many others. Each one is a great gathering of galaxies, stretched across vast distances, connected by filaments to other gatherings. The whole pattern continues outward as far as we can see, into the deepest reaches of the observable universe. And between the filaments are the voids. The largest known void, called the Bootes void, is about 330 million light-years across, a region of space almost entirely empty of galaxies. There are other voids of similar size. The cosmic foam, when you map it at the largest scales, is mostly empty. Most of the universe is in the voids. The bright galaxies that we usually think of as the universe are actually a small minority of the cosmic real estate. They cluster along the filaments, leaving the great empty voids between them. We live then in a small bright filament inside a much larger pattern of bright filaments and empty voids. Above us, in the perpendicular directions, the cosmic web extends in every direction we can see. We can look out and see the bright galaxies along nearby filaments. We can look out and see the dark voids between them. The pattern is everywhere. The cosmos is structured at the largest scales into this great web of filaments and voids, and our small, bright home is one tiny mote of light along one filament in the great structure. The perpendicular directions we have been exploring tonight, when extended far enough, eventually lead us into the cosmic web, into the great, soft architecture of filaments and voids that fills the universe. The up and the down of the solar system, after billions of light years of patient travel, would deliver us to the deepest structure of the cosmos. We are nestled inside the cosmic web. We are part of it. We are one small bright point in a great soft pattern that fills the whole universe. So as the night deepens around you and sleep draws near, let us gather everything we have understood together, gently, into one last quiet thought. You live in a flat solar system, a disk of planets, a thin sheet of marbles orbiting the sun. But the solar system itself is just a small, bright sliver inside a great spherical shell of icy comets called the Oort cloud, which extends in all directions, including up and including down. Above your solar system, perpendicular to the disk in which Earth orbits, there are trillions of small icy bodies drifting in patient orbits, waiting in the dark, sometimes one of them being slowly nudged inward to become a comet that briefly visits our skies. Below your solar system, perpendicular in the other direction, the Oort cloud continues, the same shell, mirror-imaged, with the same trillions of icy bodies, drifting in the same patient orbits. We are surrounded above and below by the most patient features of our cosmic home. Soft, icy survivors from the earliest days of the solar system, holding our matter in cold storage, drifting in the dark, asking nothing of us. Beyond the Oort cloud, in the perpendicular directions, the great local bubble extends, a region of relatively empty space carved out by ancient supernovae. Beyond that, the local interstellar medium continues. Beyond that, the galactic disk gradually gives way to the much sparser galactic halo above and below. Beyond the halo, the great intergalactic dark begins, with dim companion galaxies orbiting our Milky Way in the perpendicular directions. Far above us, in directions perpendicular to our galactic plane, lies Andromeda, our nearest large galactic sibling, slowly drifting toward us through the dark, fated to merge with us in 4 billion years. And beyond Andromeda, the great cosmic web, galaxies clustered into filaments and walls, separated by vast, empty voids, stretching for billions of light years across the observable universe. So as you drift toward sleep, let the perpendicular directions hold you gently. Above you, soft, icy comets drift in patient orbits. Below you, the same. Above the galaxy, dim companion galaxies orbit slowly, dark with starlessness, but full with the patient mass of dark matter. Below the galaxy, the same. Above us all, in the long perpendicular direction, our sister Andromeda drifts toward us through the dark, taking 4 billion years to reach us. Below us all, the great cosmic web stretches into the deep, full of galaxies we will never visit, but which exist, drifting patiently, doing the slow work of being themselves. You live in a cosmos populated in every direction. And tonight, while you rest, all of it is doing exactly what it has always done. Gently, in the soft directions we almost never look. Good night, icy comets above us. Good night, dim companion galaxies. Good night, soft sister Andromeda drifting through the dark. Good night, perpendicular directions of the cosmos. Good night, you.